Let's start operators. Operators represent observables like position, momentum, etc. We will discuss in detail about linear operator, but first let's have an overview of some basic properties of operators. An operator can operate on Kate vector or bra vector. If it operates on a Kate vector, it acts from the left side. And if it operates on bra vector, it will be acting from right side. If this relation follows that for any arbitrary Kate state alpha, x cap alpha equal to y cap alpha, then we can write that these two operators are equal. If any operator x operating on alpha gives us 0, that means x is a null operator. Operators can be added, can be multiplied also. Operator addition is commutative and associative. This is commutation property, x cap plus y cap, or you may call it hat, x hat plus y hat equal to y hat plus x hat. And this is associative property of operators. There is an exception of time reversal operator where this do not hold. We will come in detail after a while. If an operator satisfies this relation where C alpha, C beta just are constants, C alpha is a complex constant, C beta is a complex constant, alpha is an arbitrary state, beta is an arbitrary state. So if an operator x operates on this set like this, then this complex number will be unaffected, will be not operated by the operator. So we can take this coefficient, this number Ca out, and this operator will be acting on the Kate vector only. Similarly here, the x operator operates only on the beta vector only, beta Kate vector only, but the coefficient C beta remains unaffected. If an operator satisfies this relation, that if we make operator is a matrix actually, and if we make transpose of a matrix, that is we make rows into columns or columns into rows, and we make the complex conjugate of the individual components of that matrix, but still we have the same matrix, then we can call it this operator an Hermitian operator, and this procedure is called Hermitian adjoint of an operator. Let's start the discuss of linear operators. We have studied some basic properties of operators. What is a linear operator? I will define that, but take for example, for the time being, suppose rotation is an operator. What does it do? I have a vector A, I apply rotation here, it changes its direction by 90 degree and it becomes another vector, a new vector, which is A1. So rotation is an operator. This is an operator in 3D. But we are now in a complex vector space. We are not in Euclidean space now. We are in a complex vector space with n discrete dimensions, in discrete components. Properties of linear operators are operator O operating on a Kate vector gives us a new vector B, just like this rotation. Like the rotation applies on A gives us a new vector A1. Property 2, suppose A is a vector, alpha A is also a vector. Because multiplying a vector with a number does not change the vector. It only alters its length but not the direction. So the vector is still A. So vector A and vector alpha A are basically the same. So when we are applying the operator from left side on alpha A, things will remain same. This complex number, this is a number, the operator will not operate on the complex number. So I can take this complex number outside and the operator O will operate only on the kth vector A. For example, if O is rotation operator, this operator operates only on the direction. It changes the direction only but not the length of the vector. Now this operator operating on A plus B, the summation of these two vectors. First it will apply on A, then plus it will again apply on B. These are the property, these two are basically very two important properties of linear operator. These are signature of a linear operator, to be more precise. Now let's take equation 1. What is an operator O? What is the form of this operator O? This operator O is basically a n by n matrix. So it is a matrix with n square elements. So what I am doing here is I am doing a matrix multiplication. This is a column matrix. I am multiplying this column A matrix with this n by n matrix, and it gives me another column matrix B. What happens when I sandwich this operator O with a column vector and a row vector Ek? This is my base vector here. I have already discussed the basis vectors. From equation 1, O operating on A gives us B. So I can write B here, B kth vector here, and Ek, that is in the basis Ek, the kth vector B will give us the component Bk. This is a component. This is component of vector B. We have already discussed how to calculate component in any basis vectors. Let's define a very important relation which is known as completeness relation of basis vectors. We will exploit this property and this relation again and again. If I write the basis vectors like this is called outer product, and with the summation sign of I equal to 1 to n, I will get another operator I hat, which is basically an identity matrix. So for a vector A, I can write this identity matrix into A, because if I multiply identity with a vector A, things will not change. Something multiplied with 1 gives me back that particular thing, the previous thing. So I have just inserted the identity operator, the whole thing. Here I have already this kth A vector. And by the definition of components for this basis vector Ei, this scalar product, that is Eia, will give me the component Ai. Ai is a complex number, so I can write it wherever I want. This is a number. Position does not matter here. So I am writing this component Ai here, and my base vector is Ei, summation I equal to 1 to n. This is completeness relation. What does it tell? It tells us that if Ei is a basis vector and it is a complete set of basis vector, it forms a complete set of vectors. I can write any vector A as a linear combination of all these basis vectors, that is in n dimensional. If these basis vectors form a complete set, then any vector A in this dimension can be written as a linear combination of these basis vectors. from property 1, I can already write this. I have just discussed this also, that is O operating on A gives me back this B. So it is just the component Bk in this basis vector Ek. Let's find out the component of B ket vector Bk in the Ek basis. First I am using this because I have shown that Ek OA equal to Ek. Now OA is by definition Bk, and by the method of finding the component, you can have a look there. I can write this EKB scalar product as the component Bk. So I am starting with this EKOA here. I can put identity operator anywhere I wish, because multiplying with identity with A is basically leaving the ket vector A itself. So I have inserted the identity operator here. Just use the expression of the identity operator. Now in the second line, EIA is nothing but the component of A vector in the EI basis, which is nothing but AI. This summation has nothing to do with this ket or bra vector. It's just a notation, just a process, so I can take it outside. This is a complex number, so I can write it wherever I want to write. So I am taking it here in front. I am left with EKOEI, and this is defined as OKI. That is, the matrix O is written in the two base vectors EI and EK, and this is the kith component of this operator O. So I am left with sum over I equal to 1 to n OKI AI, and this is equal to Bk also. So I can write Bk equal to this, which means if I have the ket vector and the operator O itself, then I can find component of any vector. It could be Bk, it could be Dk, it could be Ik, whatever I want. And I and k both run from 1 to n, because we are in an n-dimensional basis. In metric notation, this relation will take the form like this. A is a complex matrix, which means it is a set of n complex numbers. O is a n by n matrix with n square elements, complex elements. So it is a n by n matrix, and what I am getting this, when we operate this matrix on this column matrix, I am getting this another new matrix which is new one, with again n number of complex element. But we cannot operate O on this ket vector from right side. We need to operate it from left side always. This is illegal. So what we have learned so far is we have learnt about the basis vectors. We have learnt about the orthonormality property of the basis vectors. If I put delta Ik when I equal to k, that means delta Ik equal to 1, that is the orthonormality condition. And if I put I not equal to k, delta Ik will give me 0, that is the orthogonality condition. That means Ei and Ek, these two basis vectors, are perpendicular to each other. Just like in the Euclidean space, we have found that I dot j equal to 0, j dot k equal to 0, but I dot I equal to 1, j dot j equal to 1, k dot k equal to 1, etc. From the completeness, we have learnt about this identity operator. I can write the identity matrix, identity operator, as the outer product of the basis vectors, and as they are complete in nature, as these basis vectors itself form a complete set. So any vector A can be written as a linear combination on these basis vectors. So this is my completeness relation. So in order to write this completeness relation, I am here starting with the kth vector itself. If I write A, then when I multiply identity operator from left side, I am left with this equation, this term. This is completely okay. Now, if I make the scalar product of EI with the kth vector A, it looks like this, and this scalar product is nothing but the AI component itself. So what I am getting here is the kth A in terms of the basis vectors as a linear combination of the basis vectors and the component of A itself. This is the completeness property of the basis vectors. Let's have a look at the power of the identity operator. With this problem, I have a projection operator P hat which satisfies the relation P square equal to P hat. I have this basis where I runs from 1 to n. So I can, with this information that I runs from 1 to n, I can say that I am now in n-dimensional basis. If I equal to 1, 2, 3, 4, 5, then I can say that we are in a 5 dimension. And this form a complete orthonormal basis so that we can use the identity operator. Now we have to show that Pi hat equal to EI, that is the outer product of these two basis vectors. And we have to show that this Pi is also a projection operator. Second problem is we have to verify that when I is not equal to j, then Pi plus Pj is also a projection operator. Now this is the property of this projection operator for this problem, that P square equal to P, which means if I need to show that Pi is a projection operator, then I need to show Pi square equal to Pi. So for case 1, I am utilizing the property of the projection operator and the definition of the projection operator given in the problem to show that Pi is also a projection operator. So basically we need to show Pi square equal to Pi hat. For Pi square, I can write Pi. I have actually not used this hat, but it is recommended to use this hat for operators. So in place of Pi, I have used their definition given in the problem. And as they are forming a complete orthonormal basis, these EI vectors are forming a complete orthonormal basis. So using the orthonormality property of them, I can write EI equal to delta II. If it is EI, then I need to write delta Ij. This I have already discussed before. So for EI scalar product, I can write delta II. Now delta II is nothing but delta, that is the property of Kronecker delta. So I am left with EI, which is nothing but this projection operator Pi itself. So my case 1 is proved. For the second problem, I need to prove that Pi plus Pj is also a projection operator. That means we need to prove that Pi plus Pj whole square equal to Pi plus Pj. Now let's start. For Pi plus Pj whole square, I can write this. So I need to multiply it. Multiplication gives me Pi square plus Pj square plus Pi Pj plus Pj Pi, as these are operators. So order of operation is very important. So I can't just write it as 2 Pi Pj or 2 Pj Pi instead of writing Pi Pj plus Pj Pi. Now I have just proved in my case 1 that pi square equal to pi and pj square equal to pj. Now I am using the definition of the projection operators pi equal to the outer product of ei and pj equal to outer product of ej. Similar is the case here in the fourth term. Now I need to exploit the orthonormality property of these basis vectors. Ei will give me delta ij. Similarly, ej in the fourth term will give me delta ji. And if I is not equal to j, which is given here in the problem for the second case, this turns out to be 0. So this third term and the fourth term will vanish. Here I am using the property of Kronecker delta. So I am left with pi plus pj, which means it is pi plus pj whole square equal to pi plus pj, which is the definition of the projection operator. So I have proved that pi plus pj is also a projection operator.